The universe is a vast and mysterious place. For centuries, we've gazed at the stars and pondered our place in the cosmos. We've made incredible strides in understanding the laws that govern the universe on a grand scale, from the motion of planets to the birth of galaxies. But what about the universe at its smallest level? What are the fundamental building blocks of reality? This is where we enter the strange and counterintuitive world of quantum mechanics. Quantum mechanics is a branch of physics that studies the behavior of matter and energy at the atomic and subatomic levels. It is a world where the familiar rules of classical physics no longer apply, a world where particles can be in multiple states at once, where information can be teleported across vast distances, and where the very act of observation can influence the outcome of an experiment. Quantum mechanics may seem like science fiction, but it is a very real and fundamental part of our universe. In fact, it is the foundation upon which all of modern physics is built. Without quantum mechanics, we wouldn't have lasers, transistors, or even the ability to understand the behavior of stars. To understand the strangeness of the quantum world, we need to first understand how it differs from the world we experience every day. Classical physics, the physics of Isaac Newton and James Clerk Maxwell, describes the world we see and interact with. It's the physics of baseballs flying through the air, planets orbiting the sun, and electricity flowing through wires. In the classical world, objects have definite properties. A ball has a specific position and momentum. We can measure these properties, and our measurements don't affect the ball itself. Quantum mechanics throws these classical notions out the window. At the quantum level, particles like electrons and photons don't behave like tiny billiard balls. Instead, they exhibit wave-like properties, spreading out like ripples on a pond. Their properties, like position and momentum, are not fixed but exist as a range of probabilities. They don't have a definite location until we measure them. Even more bizarre, the act of observing a quantum particle affects its state. This fundamental uncertainty is a key principle of quantum mechanics. It tells us that at the most fundamental level, the universe is not deterministic but probabilistic. This might seem unsettling, but it's this very uncertainty that leads to the incredible diversity and complexity of our universe. One of the most mind-bending concepts in quantum mechanics is wave-particle duality. Particles like electrons and photons can behave like both waves and particles. The double-slit experiment demonstrates this duality. Photons create an interference pattern, characteristic of waves. This is wave-particle duality in action. Another bizarre consequence of quantum mechanics is the concept of superposition. This is the idea that a particle can exist in multiple states at the same time until it is measured. It's like flipping a coin. It's both heads and tails until it lands. This concept is famously illustrated by Schrödinger's cat thought experiment. Imagine a cat inside a sealed box. Also inside the box is a device containing a radioactive atom and a vial of poison. If the atom decays, it triggers the device, breaking the vial and killing the cat. However, if the atom doesn't decay, the cat remains alive. According to quantum mechanics, the radioactive atom exists in a superposition of states, both decayed and undecayed, until we open the box and observe it. This means that the cat is also in a superposition of states, both alive and dead, until we open the box. Of course, this is a thought experiment, and no actual cats were harmed. It highlights the strange nature of superposition, where a system can exist in multiple states until a measurement forces it to choose one. Perhaps the most mind-boggling phenomenon in quantum mechanics is entanglement. This occurs when two particles become linked, even when separated by vast distances. Imagine two coins flipped simultaneously, one landing on heads, the other on tails. In the quantum world, we can entangle two particles so they are linked in this way. If we measure one particle and find it in a particular state, we instantly know the state of the other particle, no matter how far apart they are. This instantaneous connection baffled even Einstein, who famously called it spooky action at a distance. He believed there must be some hidden variable we weren't accounting for, something that predetermined the particle's states. However, experiments have repeatedly confirmed the reality of entanglement, showing that the universe is far stranger than even Einstein imagined. Entanglement has profound implications for our understanding of the universe. It suggests that information can be transmitted instantaneously across vast distances, potentially even faster than the speed of light. While we are still far from Star Trek-style teleportation, Entanglement is a key resource for developing groundbreaking technologies like quantum computers and secure quantum communication networks. Another fundamental principle of quantum mechanics is the uncertainty principle, formulated by Werner Heisenberg. This principle states that there are certain pairs of properties of particles, like position and momentum, that we cannot know with perfect accuracy simultaneously. The more precisely we try to measure one property, the less we know about the other. Imagine trying to determine the exact position and speed of a moving electron. To measure its position, we need to interact with it, perhaps by bouncing a photon off of it. However, this interaction will inevitably alter the electron's momentum, making it impossible to know both with perfect certainty. The uncertainty principle isn't a limitation of our measuring devices, it's a fundamental property of the universe. It tells us that at the quantum level there is an inherent fuzziness to reality, a fundamental limit to what we can know about the universe. However, this uncertainty is not a negative, it's what allows for the incredible diversity and complexity of the universe we live in. Quantum mechanics may seem like a strange and esoteric theory, but it has had a profound impact on our lives. Many technologies we rely on today, from lasers to smartphones to medical imaging devices, are based on the principles of quantum mechanics. One of the most well-known applications is the laser. Lasers work by exploiting the quantum property of electrons to exist in specific energy levels within an atom. By exciting electrons to higher energy levels and then stimulating them to drop down to lower levels, we can generate a beam of light with remarkable properties. It's coherent, meaning all the light waves are in sync, and monochromatic, meaning it's all the same color. Lasers are used in everything from barcode scanners to fiber optic communications to laser surgery. Another area where quantum mechanics is poised to revolutionize technology is quantum computing. Quantum computers exploit the principles of superposition and entanglement to perform calculations that are impossible for even the most powerful classical computers. While still in their early stages of development, quantum computers have the potential to revolutionize fields such as medicine, materials science, and artificial intelligence. Quantum mechanics is a mind-bending and counterintuitive theory that challenges our very understanding of reality. It tells us that the universe is far stranger and more wondrous than we could have ever imagined. It's a universe where particles can be in multiple states at once, where information can be teleported across vast distances, and where the very act of observation can influence the outcome of an experiment. While we've made incredible strides in understanding the quantum world, many mysteries remain. We're still grappling with the implications of entanglement, the nature of quantum measurement, and the search for a unified theory of physics that can reconcile quantum mechanics with Einstein's general theory of relativity. The quantum frontier is vast and unexplored, promising unimaginable breakthroughs in our understanding of the universe and our place within it. As we continue to probe the depths of the quantum realm, we are constantly reminded that the universe is full of surprises. The more we learn, the more we realize how much more there is to discover. The journey into the quantum world is a journey into the very heart of reality, a journey that promises to transform our understanding of the universe and our place within it for generations to come.